or the Google Shuttle, or the Google Prius, or the Google Horse, or the Google Bicycle, and go to the Google data centers. And some of them, fewer still, will walk the Google data center aisles and find that some of the more than 3 million Google enterprise-grade servers deployed in Google data centers all around the Google world have Google died. And they don't Google care. They didn't care when they got the notification that those servers died at 8 in the morning, and they certainly don't care now at 4 in the afternoon. They don't care because they didn't build their services to be sensitive to the loss of a few nodes. That's why they're Google. We need to do the same thing. We need to understand that at sufficient scale, things will break. High-performing organizations understand this fact implicitly. There are people at Netflix that understand this. Netflix and many other organizations like it have a very simple model. They say, you build it, you run it. At Netflix, they're zealous about this. They built a suite of software components called the Simian Army. Simian being a $5 word for monkeys. It's their monkey army. The Simian Army is a suite of components that they built to wreak havoc on their production systems, to create chaos. They have different agents that, when loosed into a production environment, kill processes, block ports, RMRF database and disk partitions. They even have one called Chaos Kong. And Chaos Kong gives me goosebumps as I pronounce its name. It purposefully and utterly kills a whole data center availability zone. They do this to themselves on purpose during office hours because they want to know that when a service fails, or when a service is going to fail, that they find out about it and they can fix it. They do this to themselves during office hours when there are developers on hand because they'd much rather find out at 3 in the afternoon than at 4 in the morning. They understand that things will fail, and they don't want people going to sleep confident that, oh, it's not their problem, somebody else will take advantage, take the situation and handle it. These organizations and many others have a very simple motto. They say, you build it, you run it. It doesn't matter what technology you use to solve the problem at hand, but when something goes south at 4 in the morning, you get to handle it. You get the phone call. There's no wall over which you can throw your terrible code and it's somebody else's problem now. You deployed it, it's your problem, right? That day is gone. We now talk about this idea of operations, and developers. We used to say, oh, well, the developers are the ones who are charged with delivering new business differentiating functionality. They're the ones that have to go fast. They're the keepers of the business value. And operations, they're responsible for ensuring the stability of the production system. We used to think of these things as being mutually exclusive. And that's why there's this tension, or there was. Nowadays, we talk about DevOps, right? DevOps, of course, as you know, being here in Europe, where the history is, you know that DevOps is an ancient Greek word. It means empathy. Empathy for other people in the team. Empathy for other people in the organization. Empathy for yourself, because you're the one who's going to get the phone call. DevOps is this idea that there is no wall over which you can throw your terrible code. There is no breakdown between responsibilities. Operations is just as responsible for ensuring new business functionality at a timely manner, and developers are just as responsible for ensuring production stability. These things are not mutually orthogonal. You build it, you run it. So while this is going to do the right thing in the 80% case, it's still going to fail in some of those cases, and we shouldn't sleep comfortably ignoring that. We need to be a little bit more robust. We have this endpoint here. We're going to call this reservation service. 80% of the time, that's going to work just fine. But at some points, that may not work, and we need to degrade gracefully. One way to do that is to bring in the circuit breaker. And I've got Netflix Hystrix. This is on the class path here. So I'm going to wrap this call, this reactive call, into a circuit breaker. I'll say Hystrix commands. Dot from, passing in the names, and build. So I'm going to wrap this into a circuit breaker. The circuit breaker is going to be eager. It's going to have a command name called names, let's just say. I'm going to have a fallback behavior. And so the circuit breaker, when something goes wrong in making that call, it's going to see the exception, and it's going to return a hard-coded publisher that we're going to give it. And that adapter is what we're going to return to the client. So now, happy path, no problem, everything's fine. Making the same request over and over and over. Now let's go kill our poor reservation service. Goodbye. Cached a few seconds, there we go. Eek. Okay? So I made the request, and what I didn't get is a big 500 error, or a big Java stack trace, right? I didn't get a big giant ASCII middle finger. Instead, what I got is the response I expected. High-performing organizations do this kind of thing all the time. They'll say, oh, well, you called the search engine service, but the search engine service isn't available right now. So here are some machine-learned recommendations from across the web. Is it what you wanted? Well, probably not, but it's better than nothing, certainly. Right? And from the perspective of the client, nothing is the matter. We have to build systems predicated not on the assumption that every service will be available all the time, but instead predicated on the assumption that we can remediate the service. If, from the perspective of the client, it takes 0 seconds to either load balance to another node or spin up a new virtual machine or to do something in lieu of failure, then we are effectively 100% highly available. 100% highly available. We cannot build systems predicated on the lie that everything will be available all the time. It's very difficult to get one node of one instance available for 5 nines of availability. It's virtually impossible to get it available for 100%. So to build a system predicated on the lie that every node is going to be available is just insane. At sufficient scale, something will always be on fire. It has been more than a decade since Google has had one day where something wasn't on fire. Something wasn't broken. There hasn't been a minute of any day ever in the last 10 years where these companies haven't had something broken. Same thing for Netflix, same thing for Twitter, same thing for everything. And they understand that. So this circuit breaker is smart. Eventually, once that service comes back online, it's going to invalidate its local cached perspective of the services in the registry. Hopefully you've got something like Cloud Foundry. Cloud Foundry will move heaven and earth. If you say, I want 10 instances of this service to run at all times, it'll make sure that, darn it, there are 10 instances of that service at all times. It'll make sure that service is available as much as possible. If it falls down, it'll pick it back up again. If it falls down again, it'll pick it back up again. It's like you when you have your drunk friend at the bar. It'll make sure that your service gets in their taxi and goes home. But it's our job as developers and architects to make sure that we build our services to do the right thing in the meantime. So that's what the circuit breaker does. Now, this is the read use case. I'm reading data from the downstream service. What about write? What about writing data? What if I have another endpoint here, and this endpoint on the client supports a post? Reservations. What do I do then? I could use the web client. I could use the web client to post the request to the downstream service. But what if that downstream service isn't there? What if it's not available? I can't really, that would defeat the whole point, right? I mean, I can't just post to the service if it's not available. And I can't just hold the data, right? I've got to do something with it. I can't just drop it on the floor. This isn't MongoDB. I can't just lose data for no reason, right? I've got to do something with it. Even a little child, even a 4-year-old child knows if you take something that doesn't belong to you and then run away with it, it's bad news, Mongo. It's bad news. So we need to do better. Literally, the first year of computer science would have taught us that, Mongo. So, instead of doing that, instead of just losing data for no reason, we need to send this data somewhere where the write will be absorbed and then delivered to the service that can process it eventually. And there's a lot of ways to solve this problem. This is not a new problem at all, right? This is a 50-year-old idea, 60-year-old idea. As soon as there were 2 computers, somebody had to solve this problem. And of course, there's a lot of patterns we can use to solve this, right? One of them is messaging, which is not even a controversial idea. Eventual consistency, which is just a $5 word for messaging. We could look at the Saga pattern. The Saga pattern is certainly one option. The Saga pattern is a 30-year-old idea. The Saga pattern originated in the context of a long-running transaction on a single node, during which you wanted to avoid idle resources. But what is a network partition but a function of time? The Saga pattern works just fine for our use case. It's a little bit more complicated than what we need here, but I encourage you to check it out. It's a really useful pattern in this particular case. For our purposes, though, messaging will work just fine. We're going to send a message and deliver it via some sort of message queue, a broker of some sort, and then the consumer will consume or absorb that right when it can. I'm going to use Apache Kafka, and it occurs to me as I write this, as I stand here, that I don't have that running in the background. So let's go ahead and do that. I'm going to go to Apache Kafka, and I've got a zookeeper, got to go for that, and we're going to have kafka.sh, go for that. All right. So there we go. So now I'm going to use some sort of messaging technology to talk to Kafka. And I could use Spring integration. Spring integration is a very nice technology for this particular use case. It lets me describe the connection between different services using message channels. A message channel is a pipe. Data goes in, data goes out. Very simple, right? It supports the pipes and filters architecture for messaging. You can connect the components on either side of these pipes to brokers. You can talk to disparate sources and sinks, things like FTP services and Twitter and email and Kafka and JMS and RabbitMQ and whatever, right? The whole world of input and output, you can imagine there's an adapter for that. You have to configure it, though. And if you want to do that kind of integration, then that's fine. Spring integration is a very nice fit. But we're not trying to, it's 2018. We're not going to use an FTP server for our microservices to talk to each other. I'm not going to put the response from one service, I'm not going to deposit it into an FTP server for another microservice. That's more of a, what I would have done yesterday. That's more of a older pattern. It's 2018. I can take for granted that I will use a highly available, transactional, highly concurrent, highly scalable message queue, something like RabbitMQ or Apache Kafka. And if I can take that for granted, then I should. And I can move up the abstraction stack a little bit. I can use Spring Cloud Stream. Spring Cloud Stream builds upon Apache Kafka. It builds upon Spring integration, and it uses support for. It supports things like Apache Kafka and RabbitMQ, and it does so by way of a binder. A binder is a dependency that allows Spring Cloud Stream to work with an underlying broker, like in this case Kafka. So I've got Spring Cloud Stream binder Kafka, and in my code I need to describe the binding, and the way you do that is with an interface definition. So here's my producer. This is the client, right? I'm going to say producer channels, fun output, message channel. Right? I'm going to say at output, and I can name this at output as well. I can create as many channel definitions as I want. I can say fun orders. This is the order service, for example, and at output orders. I can have as many as I want. I can name them whenever I want. The name in the code is immaterial. We have to connect that to a broker, but we do so through configuration. And in order to use this, you just say at enable binding producer channels. Okay? That's certainly a common enough thing, by the way, that at this point, the Spring Cloud Stream team already provides a source.class. And source.class does exactly that. It's got a definition for an output channel, and it's annotated with that output, and it's got a string literal called output. So I can actually use source if I don't want to create my own. So get rid of that. And now, with that in place, I can actually inject that source into my messaging endpoint here. Val source equals ref source. And here, I can say source.output.send. I'm going to send a message. So what I want to do is I want to take the incoming request from here. Right? That's it. I'm going to say request dot body to flux to a reservation. I'm going to unpack the reservation. Okay, map it.reservation name. I'll turn that into a another object here that we're going to, just in case, so it's clean. So reservation name will be it. Oh, no, actually, I just want to leave it. I want to unpack it. So then I'm going to take that and I'm going to turn it into a message. Message builder.with payload it. In this case, it is a string. Yelling at it. build. And then I want to take that and send it. So I'll say source.output.send it, where it is the message. And then finally, all of that I'm going to send back to the client of the post. So the body, val sent publisher of Boolean. All right, so I'll say that. Good. So I'm taking the incoming request, I'm turning it into a publisher, mapping it, turning it into a Spring Cloud Stream and Spring Integration and Spring Framework message, and sending it on the output channel that I've defined in the source definition up here. And I can actually just cache that dependency there. And of course, this is the, I can just do it. Okay. And now that we understand what that is, we can get rid of that. And there you go. Good. So that's my producer. When the request comes in, I'm going to turn it into a message and send it on the output stream. Let's go ahead and restart this. And on the consumer side, I want to do the same thing in reverse. So let me go back to the build, and I'll bring in Spring Cloud Stream Kafka here. All right. And I can do the same thing in reverse. I'm going to use @enable binding, and I'll use a sync. Whoops. Alrighty. Now, in the sync side, I want to consume data. So sync has an input channel. That's a subscribable channel, takes an input. And I'm going to consume data that's going to be delivered. So on this side, I'm going to create a stream listener that's going to take incoming data, stream listener, fun, incoming, and the names are going to be a publisher. So normally when you use Spring Cloud Stream, you say just string, for example, right? String, name, whatever. And Spring Cloud Stream will call your method. If you say it like this, you can say sync.input. Normally Spring Cloud Stream will call this method as many times as there are messages arriving off of Kafka. In this case, however, I'm telling it to give me a publisher of strings, of messages coming off of Kafka. So each time there's a new message that arrives coming off of Kafka, sync.input. Each time there's a new message arrives coming off of Kafka, a new item will be emitted from this publisher. So I'm going to say names dot map it, and this is the string. So I'm going to take that and turn it into a reservation. Reservation name equals it, map, and then I'll send that. And I'm going to actually, I've already got that. I'm going to now save it into the database. So I'll just inject the reservation repository. All right, reservation repository dot save it, and then I'm going to subscribe. So I've got the results. And what do I actually have here? I have it is a mono. So I want to actually do flat map. So here we go. Print line saved it.id having name it.reservation name. Cool. Okay. So this is my consumer, my reactive messaging consumer. Now, in order to understand how this is happening, take a look at the configuration in the config server. Localhost 8888 reservation client default. Here it says Spring Cloud Stream bindings.output.destination equals reservations. Output is the name of the channel. Reservations is the name of the Kafka topic. Both producer and consumer need to agree on this part. So here's the service. There's the client. On the consumer side, it says Spring Cloud Stream bindings.destination input.destination equals reservation. So mirror image, right? It's the parallel. Notice that there is no connection between the Java code and the Kafka topic. This indirection is done in the configuration, in the property files, and you can change that later on. If you want to string together service A to string B to talk to service B to talk to service D, you can reconfigure that later on. It's in the config. It's not in the Java code. Now, when a message arrives, when a message is sent in your Spring Cloud Stream binding, it is publish, subscribe, broadcast, one to many. So you're going to send one message. If you have 10 consumers, all 10 consumers will get the same one message. So it's redundant. It's broadcast, right? But I can say that I want them to be a part of a group. And in this case, only one consumer will get one message, right? Only one consumer of all the 10 consumers will get any one message. So now I'm load balancing. So that's what I've did. I've said that they're all part of a group called the reservations group, and you can call it whatever you want. I've just called it reservations group. And then finally, if there are 0 consumers, I want to make sure I process any missed. I want to make sure I've processed any missed messages. So here it says input.durable subscription equals true. So now let's see what we got. Curl minus d curly bracket minus h is going to be content hyphen type application JSON. Eh?
The TV is about to turn off.
Awkward.
Wi-Fi is already gone.
Thank you. Okay. Reservations. Reservation name. Foo. Dr. Seuss. So I'm going to send some of my favorite doctors to the service. Okay. So now, if I go to here, oh, that's the client. Where's my consumer? Ruh-roh. Sync input. Stream listener. Oh. It's the wrong one. Okay, so CloudStream reactive, is it? Okay. This is the service. Restart. Okay, so there we go. It's it retroactively processed the missed message. I sent the message via the producer. It arrived in Kafka, and when I restarted, it retroactively consumed the message I missed in the last time because I had the wrong jar on the class path. But let's just try it in the happy path again. I'll send some more of my favorite doctors. I sent Dr. Seuss, Dr. Strange, Dr. Who, Dr. Sire, Dr. Pollock, Dr. DeVolder. All right, so we got a few of my favorite doctors, and there they all are. Good doctors reporting for duty. So you can see that Spring Cloud Stream allows us to do the right thing in the case of read failures and write failures. In the case of write failures, if I miss a message, I can retroactively consume it, just like I did in that case for the one that we lost. In the case of read failures, we use the circuit breaker. Now, as we wind down here, let's talk about observability for a minute. We talked about observability in the case of the individual node. We looked at the actuator as a way of surfacing information about any particular endpoint, about any particular application. And that works just fine. But we're missing the larger picture. Our system has behavior that is emergent that you can't appreciate by looking at individual nodes. If I'm walking here in beautiful Linz, is that experience the same thing as I would get if I were looking at the Google map of Linz? Is it identical? Is it functionally equivalent? Of course not, right? There's so much more to appreciate here on the ground that I couldn't appreciate by looking at the Google map. There's so much more to appreciate being here than the Google map could ever hope to convey. The map is not the terrain. And the same is true for your production system. Your production system is not the architecture diagram of your production system. You can't understand what your system is doing by monitoring the production diagram. You need to monitor the system itself. And one way to do that is in that circuit breaker. That circuit breaker that we looked at earlier has state. A circuit breaker, as you can imagine, it prevents the potentially overwhelming deluge of data from overwhelming the system downstream. If I have a circuit through which data is being moved, or flowing, and that service downstream can't handle it, the circuit breaker trips and it opens. It stops the further conduction of data. It prevents the downstream service from being overwhelmed. If that service is offline and you've got something like Cloud Foundry, it'll eventually get restarted. But while it's coming back into life, the last thing that we want to do is to start hitting it, to barrage it with too many requests. We all know that when a website is failing to respond quickly, the best thing that you can do is just to refresh the browser a lot, right? Of course not. Same is true for a production system. That circuit breaker protects your downstream system from being overwhelmed. And that circuit breaker is stateful, like I said. Eventually, that state will go back to closed, and the data will go through it again. That's what we saw earlier. I restarted the service, and eventually it healed itself. But in the meantime, we want to be able to visualize what that's doing. So we can create a circuit breaker dashboard. Or not. Yes, we can. So, Hystrix dashboard. Config client, Eureka discovery, and go. UAO Hystrix dashboard. So, Hystrix dashboard. At enable Hystrix dashboard. Application.name, Spring application name equals Hystrix dashboard. All right. So that circuit breaker dashboard is going to start on port 8010. And it's going to expect as its input a service end event heartbeat stream. That heartbeat stream will come off the node that has the circuit breaker, which is the client. So we'll go to the reservation client, and we'll say at enable circuit breaker, and we'll restart. Take some tea. Localhost 9999 actuator hystrix.stream. Oh, sorry. Yeah. Hystrix.stream. I don't have actuator either. You have to have actuator to make this work. Actuator, Spring, boot, starter, actuator. Okay, actuator, hystrix.stream. There you go. So that circuit breaker has the state based on requests that are flowing through that circuit breaker in the edge service that's calling the downstream service. So if I make this call, you can see that now it's showing me this information. The circuit breaker endpoint, this heartbeat stream, is the state of every of the circuit that I'm calling. It's endless. It has no end. It is infinite. It goes on and on and on and on. Forever and ever and ever and ever and ever. It is infinite. Like the oceans and the skies and the stars and the bugs in your code, just infinite, infinite, infinite. Whatever you do, my friends, and I cannot stress this enough, whatever you do, do not curl this endpoint. So we'll go to the Hystrix dashboard here and paste that in there. Hit monitor. Localhost 9999 And as we make requests on the left, you can see the moving average is trending ever upwards on the right. It's showing us the movement of data through that circuit breaker, through the downstream service, and back again. The circuit is closed. Everything is fine. If there were any trouble, though, if the downstream service were killed, then you'd see that closed, that circuit closed status changed to circuit open, and that green orb would turn into an even more ominous floating red orb. Not good, okay? So now as I throttle the gas, if I lay off the traffic, you can see it trends towards 0. The asymptote is towards 0, okay? This is one circuit breaker and one service instance in one service in the cluster, but naturally in a production system, you'll have many more of all those things, and so you can use Spring Cloud Turbine to multiplex all the different circuit breakers into one very useful dashboard at more realistic scale. Now, my friends, a couple things to keep in mind today. We looked at the circuit breaker dashboard, we looked at the config server, we looked at Eureka, we looked at Kafka, we could have looked at distributed tracing using Zipkin. We looked at a number of different things here, and I sort of created these sort of ad hoc, bespoke little example demo versions of these things. But these are the kinds of things that you shouldn't run or manage yourself. I'm a big believer that you shouldn't run software that you cannot charge for. If you have a platform that runs this stuff for you, then do that. Find a recipe, reuse it, and never have to rework this again. You should definitely not reinvent this every single time like I did on stage. The only things that matter in all the code that we've seen today are the reservation client and the reservation service. I hope you got something out of this. I hope, that as we covered this wide roving world of cloud native Java, or in this case, cloud native Kotlin, that you got something out of it. Obviously, we looked at a number of different things that define a cloud native system. A cloud native system is something that is agile. It's easy to change. A cloud native system is one that responds well to load. It does the right thing in the face of service outages and topology changes. It's elastic. It takes advantage of the elastic nature of a cloud. And of course, it is observable. That is to say, you can understand what it's doing at the individual node level and at the distributed systems level. Everything we've looked at here tonight supports all four of those principles: elasticity, robustness, observability, and agility. A cloud native system is one that is designed for production, where your customers can use it. We've looked at a number of different things here today, and I wish we had more time. I wish we could look at even more, because we've only begun to scratch the surface. We didn't even get to scratch the surface. We looked at a photo of somebody scratching the surface of a photo. If only we had more time. If only we could have spent more time on it. I wish we could. There's just so much more to talk about. What about single sign-on and federated security using Spring Cloud Security and OAuth? What about leadership election and worker node demotion and promotion using Spring Cloud Cluster and Spring Integration? What about security secrets management using Spring Cloud Vault? What about the logical conclusion to using Spring Cloud Stream to build messaging-based microservices? How do you orchestrate those at scale? How do you describe pipelines comprised of these messaging-based microservices using Spring Cloud Dataflow, and then orchestrate that across a cloud fabric like Cloud Foundry or Kubernetes? What about if you want to do function as a service based services based on Spring Cloud? You want to do functions that work in top of a function as a service platform like Amazon Lambda or OpenWhisk or Google Cloud Functions or Project Riff, our own project function as a service platform, using Spring Cloud Function, right? If we had more time, we'd look at all of that stuff and so much more. If we had more time, we'd look at testing, and actually, we're going to look at testing if you want. Do we still have time? Okay, well, if we had more time, we'd look at testing, and we'd look at the logical consequence of moving to this architecture wherein everything becomes an integration call, an integration test. My components are now connected to each other through network calls. So what used to be a fast feedback unit test now becomes an integration test, right? I've inverted the testing pyramid. Remember the testing pyramid? 80% of that is supposed to be fast feedback unit tests. Now everything is an integration test. This is a bit discouraging because we moved to microservices to gain agility, and now suddenly for every single test run, I have to deploy the whole Cloud Foundry or Kubernetes cluster. How do you get around that? How do you go faster while still having confidence in your tests? You use Spring Cloud Contract and consumer-driven contracts. And for that, you can find Bootiful testing, Google my name and Bootiful testing, and you'll find a version of that talk that'll kind of get you to where you're supposed to be on tonight. If we had more time, my friends, we'd cover all this and so much more, but I'm afraid we're just about out of time. Now, I certainly hope you got something out of this. I certainly hope you learned something new. Did you learn anything new at all? Anybody? Okay, good. How likely are you to try any of this out? I'm just curious. Does this inspire you to want to use some of this? Okay, good. I'm happy about that. What about, do you like Kotlin? Just curious. Anybody? It's okay. Yeah. It's all that stuff is available in Java, just to be clear. It's just nicer in some cases. In some small cases, it's nicer in Kotlin. I'm a big fan of all this stuff. Obviously, I'm a big fan. I'm wearing the Spring t-shirt and Spring underwear. Obviously, I'm a big fan, right? But you don't have to take my word for it. You don't have to take my word for it. There are lots of small mom and pop organizations out there, lots of small organizations that are doing really interesting things with these technologies. If Amazon.com, if they are the Alibaba of the far, far extreme West, then Rakuten.com is the Alibaba of the extreme far, 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 far east in Japan. They're an e-commerce platform that uses Spring Boot, Spring Cloud, and Cloud Foundry to build services and to build applications that serve hundreds of millions of people at scale. Yahoo Japan is another website in Japan, actually, that's using Spring Cloud and Cloud Foundry at scale. If Alibaba is the Alibaba of the Middle East, sort of further east in the Middle East, but not as east as Japan, the middle extreme east, I don't know, whatever. If they are that, then that's pretty interesting because they're using Spring Boot and Spring Cloud for everything, and Spring for everything. They're an interesting company. I don't know if you've heard about Alibaba. Alibaba is going to be big one day. I have a hope. They're a small company right now, but one day, there are actually several companies. I should be very specific and very clear about it. They're using Spring for everything, and that's very, very interesting because they didn't start off as one big company. Alibaba, as you know today, is actually a federation of a number of different companies, each of which was ridiculously successful in its own right. Like at one point a few years ago, like 5-6 years ago, they bought a bank. Did you buy a bank? No, I didn't say that wrong. The bank didn't buy them. They bought a bank. Like they bought a bank. The people that print money, they bought that. So they bought a bank called Ant Financial, like you do. And Ant Financial, for example, is all Spring, independent of their sort of presence inside of Alibaba. There's just a number of different companies that they assimilated, and there's a number of companies that they started from whole cloth. All of that was Spring, and they started with Spring 10 plus years ago. And they had to solve problems at scale. So of course they chose Spring, because it's the only thing that gave them the flexibility to compose these pieces in a way that made sense to get them to production. There's nothing else. But nowadays, you look at all that they've done. They've had to solve some of these distributed systems problems on top of Spring. Spring 10, 15 years ago didn't solve all the things that they wanted to do. There was no support, for example, for service registration and discovery, right? So if you look at Alibaba, they even have a project called Dubbo, D-U-B-B-O. Dubbo is an open source framework that they created based on old Spring. And Dubbo, it's okay, but I have a good relationship with them. I spend about a month in China every year, just hanging out with all the different amazing companies in China building stuff on top of Spring. And Alibaba is always my favorite. They're in Hangzhou, and it's like an hour train ride from Shanghai. They use Spring for everything, and I started talking to them like 5 years ago. And I was like, 4 years ago, I guess. And I said, you've got to see the Spring Boot thing. You've got to let me show you this. The first time when I first went to go talk to them, I said, look, I'd like to show you some of the Spring stuff. And I'm sure they took my appointment because they, oh, it's him, let him in, whatever. And that was fine. But then I went and showed them the Spring Boot thing and took off like crazy. So now they're using Spring Boot for as much of this stuff as they can. They have their own eBay. They have their own Alipay. It's called Alipay. It's like eBay except it's used a lot of places, It's like PayPal, except it's used. You can go to a little hole-in-the-wall restaurant in the middle of nowhere and use your phone to buy the food. There's no it's just the menu is printed on like old paper, parchment, from prehistoric times, and it still takes Alipay. They have their own PayPal, except it's used. Like I said, they have their own B2C thing. They have their own eBay. They have their own Amazon. They have their own bank. their own PayPal. I mean, they have all these things. They have their own AWS. It's the number 3 largest infrastructure provider, infrastructure as a service provider. People think it's Google. It's not. It's AWS, Microsoft Azure, and then Alibaba, worldwide. Alibaba's they're going to be big one day. You just watch that space. So the point is that all that is Spring, and they're using it to get to production faster. There's another company in China called Baidu. They're a search engine company. They're going to be big one day as well. They're a small search engine company. They serve, the better part of 600 million plus odd people who are connected online. There's 1.5 billion people there, but not all of them are online, right? These companies and many others besides choose to build in Spring Boot and Spring Cloud and Cloud Foundry and the Pivotal ecosystem at large because they need to solve these problems. They have the money, the motivation, and the need to solve these problems, and they choose instead to build on our bits because it allows them to build better software faster, to get to production faster, to deliver software to their customers and deliver value to those customers faster and safer. And at the end of the day, that is all that matters. Thank you so much, my friends, for your time. I appreciate it. If you have any questions, I'm happy to answer them. Thank you.